I'd like to welcome Zoltán Füredi, who is one of the most established and most well-known Hungarian combinatorians, and he's a specialist in extremal graph theory and extremal hypergraph theory. And this talk is about a classical topic that goes back to the beginnings of extremal graph theory, the sort of Erdős Rényi base. So thank you very much for accepting our invitation to Moscow, and have a good time.
Thank you. I'm very pleased to be invited, and I am very happy to talk about one of my favorite topics, which has a strange name, intersecting set pair systems. So I added an extended abstract, but we can just skip it because we will see this. The main point is that I will talk about the special creatures, set pair systems, and many applications. This will be the first part of the talk to convince you that it's an important tool, and then in the second part some new results. So we are using the standard notations. Maybe the first n integers, that's a set of first integers, it's familiar. I also like to use this S choose K, not just as a binomial coefficient, but also the complete hypergraph. And here is one notation which is also quite standard. So if you have even a hypergraph, then the transversal T is a subset meeting all the edges. And tau T or tau T, tau H is the transversal number. And similarly, we have the matching number. So a matching is just a set of parallel or disjoint edges. And ops is not min but max. So we want the maximum size of a matching, and that's denoted by nu. So this transparency is mainly just to get used to my pronunciation and notations. So, and it's clear that if nu is 1, then the hypergraph has no two disjoint sets. So we call that intersecting. Okay, so let's see our starting point, Bolobás theorem from 1965. He was still a student when he did this. So we have a family of pairs of disjoint sets. That's the most important property. So we have a family of sets of disjoint pairs. But otherwise, every set A meets every, well, it's disjoint to its mate, but otherwise they intersect. The intersection is non-empty. So, so just like in this basic example, we have an underlying set X of size A plus B, and we take all the A sets, all the B sets, and pair the complements, and obviously an A set and the B set will meet except if they are complements. And this is the result Professor Bolobás proved a long time ago, that if we are given A sets and B sets, disjoint pairs, but otherwise they cross-intersect each other, then we can't have more pairs than this binomial coefficient A plus B choose A. So to tell the truth, when I have seen this statement in my professor's seminar, Gyula Katunis seminar, I saw that this is an extremely strange statement, and I only thought that maybe it is justified because it has a very nice proof. But in fact, and this will be the first part of my talk, I would like to present you as many examples as I can to prove that it's indeed an important important result and an important tool and a very useful tool. Maybe it's not no wonder that after Bolobás proved it, it was still conjectured by Berge and by others, and proved by different people independently. This standard proof, which you might have seen, goes like this. We consider the underlying set. So given the family, the cross-intersecting family, cross-intersecting set pair systems, and we consider all possible permutations of this underlying set. And we call a permutation, we give a type, it's a type I, if the elements of AI, precedes all the elements of EI. So that's the definition. And now we use that a permutation, maybe the permutation has no type at all, but if it has a type, it can have only a single type. So it cannot be type I and type J simultaneously because well, we have a cut somewhere. So if we have if both if it's I and J, then somehow one of the either AI cannot meet BJ or the other way around. And then the rest is just a little calculation. The probability that AI precedes BI is exactly comes from a binomial coefficient, because no matter where these A plus B elements are, the first A should be at the beginning. So this is 1 over A plus B over A plus B choose A. And these probabilities are, well, these events are disjoint, so the sum of the probabilities at most 1. So actually we have proved much more. We proved this nice inequality. So it's a beautiful proof, and but still, when I have seen it, I was surprised how one can come up with such an idea. But indeed, it's an important tool. And in the second part, we will consider some newer results, which are joined with my colleagues András Gyárfás and Zoltán Füredi here. Okay, so one application immediately. Actually, this application comes earlier. So whenever we have a intersecting family, we can define a kernel. The kernel is not just a cover. The kernel is a small part where all the action happens. So we can shrink the edges to a smaller set. So, for example, a kernel of a star, the usual star as a graph, is just a singleton because all the edges meet and the singleton. And the kernel of a complete graph, if intersecting, then, well, just itself. And Kaczynska-Karlowicz in '64 proved that there is a function, there is a finite value for every value r if you have an intersecting family of r element sets, then that family has a kernel which is bounded by his function. Actually, he or she, I don't know, he proved something more. It's he had a nice proof using ultrafilters. But so here is what I am talking about. So we are given a hypergraph, and which is intersecting, and we can find a smaller, usually smaller, set of vertices where the edges intersect, pairwise intersect each other. And that's true, well, only if the sets are bounded. Of course, for infinitely large sets, the kernel should be infinitely large, or could be. And for r equals 2, it's very easy because that's a graph, intersecting graph. There are only two possibilities, either a star or either a triangle. So this Kaczynska-Karlowicz number is 3. For triple systems, the projective plane shows that it's at least 7. And it was proved by Erdős and Lovász, who knew this result. They gave a new proof. Okay, so here is their proof for Kaczynska-Karlowicz. So the input is an intersecting hypergraph of R sets. And again, we consider the underlying set, the union. And we try to find the kernel by removing elements from the underlying set. So remove an element if it's possible. So for example, here we can remove all these pendant, the second vertex of the pendant edges, still intersecting. So we remove an element if it's possible. And we do this until we get a critical hypergraph where no edge can be shrunk. So that means we got an underlying set the hypergraph is still, the new hypergraph, where we stopped, it's still intersecting. And for no element can be removed, no vertex can be removed. It means that if we remove this vertex, then two edges become independent, disjoint. So they meet exactly at the vertex X. So that's what we know, and that's what we call critical. And now the rest of the proof is the same as in the previous permutation proof. We take all the permutations of the underlying set. This is not X, but now it's S. And we call it type X if that vertex, well, for every vertex we have now an AX and an X. It's not cross-intersecting, but almost. I mean, they have a singleton intersection. And all the elements of A, except one, precedes all the elements of B. And the last one is in the middle. Last one of A is in the middle. And we can calculate the probability of this event. And again, type X is different from type Y because if AX is here and Y is somewhere behind, then BY will be disjoint from AX. So add up the probabilities, it's at most 1, rearrange, we got some nice bound, roughly 4 to the R. So it's indeed actually it's a very nice bound. It's close to truth as the well. Again, the examples I am going to show you are just some basic topics where there are many new results of this very same, of this kind of I mean, about the kernel of intersecting families. I just mentioned.
Zoltán, sorry, there is a question in the chat. I don't know if you can see that.
Oh, I didn't.
Shall I read it?
The top, top or the bottom, or?
It should be at the bottom. Yeah.
Yes, here. Oh, pseudolines. Are there any relations? Relation systems of projective pseudolines. I'm sorry, I don't know that. Sorry, I don't know. Okay, so let's continue. I'm sorry, I can't answer the question, but here, Erdős and Lovász proved an exponential bound for, this is roughly 4 to the R, a bit more, and it was they found a matching, almost matching lower bound. Here is the construction. It is about the same. It's very similar, like just the intersecting set pair system example by Bolobás. So we take a 2R minus 2 element set and take all the partitions. So in every partition we assign an element outside. So altogether we will have 2R minus 2 plus a big binomial coefficient number of elements. That's the set of vertices. And now we define an intersecting hypergraph in a natural way that for every partition into even parts, into equal parts, we assign an element, and we just add that element to both sides. So it's clear that here, when we have 2r minus 2 elements and we take all the subsets of size r minus 1, that's almost intersecting, except complementary pairs. And so for every complementary pair, we assign an element outside. And this is critical. We can't shrink it. So that's the family. So they got a pretty good lower bound, which is almost 4 to the r. So, and since then these were improved, but we have no time.
Zoltán, is there
there is a better example since then.
But there is a better example, but there is this still gap of like factor of 2 or something?
So here what I presented, there was a factor r, but now the best bounds, best lower and upper bounds, actually the upper bound is now much closer to what the lower bound is, only a constant factor. Yeah, and even that constant factor is reasonably small, 2 or 3.
Okay.
So now we all learned Sperner's theorem about Sperner families, and this can be also obtained from Bolobach's inequality. Okay, so here in a Sperner family, the complementary pairs form a cross-intersecting system. Well, just jump to the next one. There are other generalizations, like we can consider k-tuples of sets, and we assign weights for every k partition. These are not really partitions, they are just k-tuples of different sets. And the most interesting one is when we consider pairs, cross-intersecting pairs. We got this nice upper bound. So if you have cross-intersecting pairs, then 2 to the maximum size of A plus B, AI plus BI, is an upper bound. The proof is probabilistic. It's, and I didn't mention in all the previous proofs, actually, or most of them, we can weaken the cross-intersection property. We have this Tuzas upper bound. Also, if we require not full cross-intersection, we want disjoint pairs. Yeah, we always want disjoint pairs. But we don't want that every A meets every other B. But for every ij pair, one of them at least should meet. Okay. Let's see a beautiful application, which is actually also older than Bolobach's result, and due to pairless. It's again a geometry application. And still unsolved, but we can see pretty good bounds now. So here in this figure, you see 4 triangles. Well, the middle one is just white, So we have 4 triangles which are disjoint, but they pairwise touch each other. Now they are tangent. Now 2 simplices are tangent if they both have a face, d-1 dimensional face, touch each other just like here, the blue and the green, not just as a vertex, but something substantial common part. But of course the interiors, I don't know what is this one here. Okay, so the interior of S and S prime are disjoint. So we have given a set of simplices or triangles in the plane. The interiors are disjoint, but they pairwise touch, and the theorem of pairless says that we can't have too many of those. So in the plane we give an upper bound 8. The truth is of course 4, and Joe Sachs proved, well, with a very tedious proof, many case studies, he proved that in 3 dimensions we can't have more than 8, and actually in every dimension we can have at least 2 to the d. So it's a kind of induction. So here basically we lift the structure and a bit rotate. So if we have a planar structure, then we lift all of them to make a tetrahedron on both directions, but then they are not tangent enough, so we have to rotate a bit. And one can do that in every dimension to get 2 to the d. And the proof is very nice. So given a family of pairwise tangent simplices, and now we list all the hyperplanes, all the faces, the facets, I mean the boundary hyperplanes. Well, if we have m simplices, we can't have more than m times d+1 hyperplanes, but even more, we are definitely less than so many, because they are pairwise touching, a pairwise tangent. And now what we do is this: we select a center somewhere, and for every triangle or every simplex, we define a set of A and a set of B. And the set of A among the hyperplanes. So the set of A are those, so take the i's simplex, and we will define a set of AI and BI altogether d+1 members of the hyperplanes, because every simplex has d+1 faces. So let's see the definition. So AI are those hyperplanes which are the boundary hyperplanes of the SI simplex, and on the same side, the simplex is the same side as O. Okay, so these are these 2 red edges belonging to that triangle. And the blue edges the other way around. Okay, so then it's a side of the triangle, but the triangle is on the different side as O, as the center. And because every 2 triangles are tangent, every simplex I and j, they will have a common line in such a way that well, they are the two triangles should be on different sides. So one segment will be blue, the other one red. So that's it, and we have the upper bound. Now, a famous generalization is due to Lovász, who extended Boloba's theorem to subspaces, so linear subspaces of a large dimensional space. So the statement is the same. We have A-dimensional spaces, B-dimensional spaces. They are paired. We cannot say they are disjoint because linear subspace always contains the zero vector, but kind of disjoint if they were together, the dimension sets up. And we got the same upper bound. And of course, it's a stronger statement what Bolobash did because we can make a geometric representation. And it's a very powerful method. It allowed us to extend the result for T-intersecting, T-cross intersecting families. Still, we do not know a non-geometric proof of this statement. So we just have a T-element set which is contained in every member here. And otherwise, we have A minus T, B minus T. So it's quite simple. But we do not know a non-geometric proof.
Zoltán, sorry, what would this kind of permutation argument give here? Would it give anything better than A plus B choose A?
Well, A plus B minus T choose A minus T.
Oh, okay.
That's what we get.
Okay.
Yeah. Now, but it's a more important consequence of Lovász method is what this theorem was proved by Peter Frank and Gil Kalai independently, that they have a intersecting set pair system, A sets, B sets, disjoint pairs, but we want cross intersection only in one direction. So it's a kind of triangular, upper triangular matrix if we do the intersections. And this can happen in many cases. So it's well, there are all kind of newer research of these, like cross intersecting other subspace versions, and Nogálon and Kalai used this result, this stronger version, to prove nice bounds, the best bounds actually, the number of faces of a convex polytope. Now, so much about applications, but how Bolobash got the problem? I mean, he apparently didn't know applications which came later, certainly not the geometric applications, and this is the way that the problem was proposed. So here is a classical definition, going back to the 1950s by Galai, that we call a graph, a simple graph, tau critical if, leaving out any edge, the covering number decreases. So, for example, the complete graph is quite clear. The covering number of complete graph is just tau. But if we leave out an edge, then we need one less. And also for the odd cycle, for example. But there are many more, and the structure was investigated by Galai. And Erdős and Galai proved if we have a graph which is tau critical, we can't have more than 2 tau vertices. Actually, here equality holds only for tau disjoint edges. Okay, quite simple. And it's more interesting, Erdős, Heiner, and Moon showed what is the maximum number of edges. Now, this is a kind of important result because this shows that to calculate the covering number of a graph is an NP problem, NP complete problem, I think. But it still shows that if tau is small, then there is a reason for it. So either we have tau disjoint edges, or at least we have a small structure, a small graph, at most so many edges, which implies that the covering number is small. So to decide that if a graph has covering number 1000, we have to consider only all the subgraphs or, well, of 2000 vertices, for example. And the proof is quite natural. I mean, actually, that's how they got the complementary pairs or disjoint pairs. That because if it's critical, that it means that for every edge, there is a cover which is only tau minus 1. And they form a cross-intersecting set pair system. And this can be extended, and that's what Bolobás did, for R-uniform families, and the same proof. Now, even in this problem, the number of vertices, the maximum number of vertices is still unsolved. So it's, you see, it's an order of magnitude smaller, just like in the graph case. Okay, so the maximum number of edges could be tau square, but number of vertices is only 2 tau, and that's the same holds in higher dimension for R-uniform families. I think still this is the best upper bound. Now I think we jump this part, and now I would like to continue with the second part. So I hope I convince you that it's an important tool, and if it's an important and useful tool, then we must investigate all kinds of versions of it. So let's see what kind of problems we investigated with András Gyárfás and Zoltán Füredi. So we call it one cross intersecting. You see that's a very, very strong extra condition. If the cross intersections are just one element set. So the cross intersections are not larger than one. Okay. So that's the one cross intersecting system. Now, well, A-B bounded is well, A sets, B sets. Now, here is a one cross intersecting system, C5, and parallel pairs. So this edge and this edge are paired, and they are disjoint, but they meet every other edge in a singleton. Or, well, with a later notation, we will state this statement as M2 is just 5. Because if we have pairs, two element sets, then Bolobash bound gives 2 plus 2 choose 2, which is 6. But that's cannot, it's not one cross intersecting. Here is another example, which is quite natural. We take an odd cycle, and for every edge, we take an independent cover of the rest of the edges. And again, these are disjoint, and obviously one cross intersecting, because an edge is never contained in this independent set, but meets it. So this is one cross intersecting, and originally we thought that well, it should be much smaller, but here is the most important figure we have found, kind of, that if we have a one cross intersecting family of size M1 of sets A1 and B1, and another one of size M2 and set sizes A2, B2, then we can kind of make a product. And we do this in the following way. We take the first family, okay, we are happy with that one, and the size of that family consists of M1 pairs, red-blue pairs, and they are one cross intersecting. And now for every pair, we make a copy of the other family. Okay, so M1 copies of the A2B2 cross intersecting family. And these are numbered. So for the ice family, the ice copy corresponds to the AI-BI pair. So AI is extended in every possible way here, and BI extended again in every possible way with the B's in the second family. Okay, so that's what is written here. Now, this will form a one cross intersecting family because well, it's just a little thinking. Let me see if we have now every new set has two parts, one in the center part and one on the side. Now, if we have AI, BI, and we have AJ, BJ, then the right-hand side are completely disjoint, so they do not count, and they are cross each other in a singleton, in in A1, B1, because that was the condition. So we have one family, cross-intersecting set pair system. So if I and J are different, then we are okay. The only problem is if we have the same I and same, and we extend in one way and extend another way. But then those sets do not meet in the first part, because we have extensions of AI here and extensions of BI here. And AI and BI are disjoint here. So they do not count, only the second part. And that's a good family again. So if we have two families, then we can make a product and we can get a much bigger family of these parameters. So if we start with 2 and 2 of size 5, then we can then we can have n half of those, I mean n half steps when we extend the families. So we always take so many copies, and in this way, okay, so if you have one pentagon and other pentagon, we can multiply them out. And the starting point are two singletons, so that's how we can have this sequence that for singletons we can have 2, for pairs we can have 5. But what is interesting, it's exponential. So at least I was surprised. It's not just exponential, it's much bigger than 2 to the n. And that's the best we know. Even we were not able to determine the case with the triples, but a younger colleague made a computer search. So we have this statement here that this mn function, the nth root is between 4 and root 5. And we can't prove the Bolobash bound at all. So it's, I'm pretty sure that the truth should be much closer to root 5. Maybe it is root 5, why not? I mean, okay, so much about one cross-intersecting families. Now, in the rest of the time, yeah, two nice topics, yeah. How we got this one cross-intersecting? Well, you see, in this, let me go back. So we have this family of size exponential and one cross-intersecting. Now, but it is spreading out. You see, in one step, I have one pentagon here and 5 here, and then I have 25 more, and so and so. So it's spreading out, and this result shows that it's not an accident. So if you have a one cross-intersecting family, then the number of edges is at most the number of vertices. Okay. So we call it Fischer type inequality. And the proof is quite natural. For every characteristic vector, well, for the set A, we have a 0, 1 vector only on the union of A. Okay. So we have a 0, 1 vector in a natural way. And we just prove that they are linearly independent. And well, we define the same way the vector B. Now, it might possible that some elements of the vector B goes out of V, the set of V, but we don't care. Okay, so we only consider V-dimensional. We consider the space R to the V. Because now, how to prove it's linearly independent? Well, the usual way. Suppose there is a dependency of the vectors of the A's, A vectors. We just multiply by one of the B's, Bj. And the dot product, because we have the intersection sizes exactly. Ai Bj is 1, except its pair. So if you multiply this by Bj, we just everywhere lambda I, except in the j's coordinate, the j's vector. So when it's 0. So if we multiply, then the dot product can be calculated. Of course, the right-hand side will be 0 vectors times 0. And the left-hand side is the total sum except lambda j. But this is true for every lambda j. So we just add this up. We got m minus 1 times the total sum. It's still 0. Well, if m is at least 2, if we have at least 2 of these, then we got this, the sum is 0. Sum is 0, every lambda is 0. That's it. So independent. So it's not a difficult proof. It's quite natural. And actually, this can be used in Gasparian's proof of Lovász theorem on perfect graphs, because maybe made a little bit faster. Basically, what we have that in a minimal imperfect graph, we have cliques, and the cliques and independent sets are just forming one cross-intersecting family. Okay. So that's the main point. Okay. Because a clique and a maximal independent set meets always in a singleton. Okay. Okay, now we went on in our research and investigated the case when A is 2, B is n, we got something. It was nice work, but what is more interesting, and that's a slightly different direction, when again we consider cross-intersecting families, but now we will suppose, well, first 2 definitions. We know what a linear hypergraph is. In intersections at most 1, just like lines on the plane. And one intersecting when the intersection is exactly 1. It's a stronger condition. And it's easy to prove how, if you have a cross-intersecting family, well, of n sets, pairs of n sets, and if one family is linear, then we can't have more than n square sets. The proof is easy, so it's not, you just have to think a little on it. So if we have a linear, one side is a linear hypergraph, then we can't have too many sets. And now we wanted to know, well, here's an example, just a this example will be size n, or not n square, but it's still, it works for every value, and n is S here. So we call it a double star. So we have blue sets and red sets of size S, exactly S uniform. And both the family A and the family B is one intersecting, and also one cross intersecting, except AI and BI are disjoint, okay, because we just left out the diagonal elements. So every AI meets every BJ except its own mate. So we have these kind of families. It's a rather simple one. And now comes a little definition. Much more general setting. So we have 6 conditions. So this function M depends on 5 parameters. A sets, B sets, or at most A sets, at most B sets. We have disjoint pairs. M of those, we want to maximize M. And we prescribe the intersections in A, prescribe the intersection sizes in B, and prescribe the cross intersections. Okay. Now, when I was a graduate student, I remember that I always skipped every paper which had a function with 4 variables. Okay, so somehow 3 variables was my limit. I mean, maybe because the space is 3-dimensional, I don't know. Or maybe because it was too much for me. But here we have 5, but it's a kind of natural definition. So basically we describe. So there is even more complex definition when we want to describe every pairwise intersection, if we can realize that. That's an unsolved problem. So, for example, it's related somewhat, but it's a discrete version of the problem that given n choose 2 distances and decide that we can have n points in the d-dimensional space, realizing these n choose 2 distances. I mean, and that's a solved problem. We can decide that it's a kind of rank of a determinant. But here we have a discrete version. We want 0-1 vectors. The sets are 0-1 vectors. Intersections are the distances, kind of. Of course, to avoid trivialities, we always suppose that 0 is not in the possible cross-intersection values, and also suppose we have at least 2 pairs. Now, we use the notation star if the constraint is empty. Okay, so if it's not a real restriction. Okay, so if we allow all kind of sizes, then we write star. So with this notation, Boloba's theorem is like this: MAB star star star, because Boloba's did not impose any restriction in the family A, in the family B, and also in the cross intersection, he only wanted positivity. And this result I mentioned earlier. And now I will talk only about families of n sets. So instead of 5 variables, we will have only 3 or 4, one in the index. And also, I will talk about linear hypergraphs or one intersecting hypergraphs. And I write it, it's just the other way around. Definition is wrong. So linear hypergraph, I will write 0, 1 intersecting. For one intersection, I will write 1, okay. So for example, the proposition I mentioned, if we have pairs of n sets, disjoint pairs, they are cross-intersecting, but the first family is a linear hypergraph, then we can't have more than n squared pairs. And what I would like to show, well, how we got this problem. It's again a large topic. We have no time to explain. This is the click partition problem. So we have seen many results when we decompose a graph into clicks, or decompose a bipartite graph to bipartite complete graphs. And usually we want to minimize the number of clicks. But here what we are interested in is not the number of clicks, but the so-called thickness of this partition, namely that one vertex how many times is covered. So that's the thickness problem of click partitions. And the two most interesting graphs, the most difficult cases, are the complete graph minus a matching, or the complete bipartite graph minus a matching, because the complete graph is very simple, it's not so we can reformulate if we are looking the thickness of this two graphs, then we exactly got this problem here, or we got exactly this problem here. This was, I already discussed, where the answer was between root 5 to the n and 4 to the n. So it's unsolved. But this one we were able to solve, and the answer will be n squared, roughly n squared. The upper bound is easy, and we want to, in the last 3 slides, I want to show you the ideas of the construction. Okay, so that's what we are, if both linear, that's okay. So these are the main results, and I want to show only this boxed statement. Let's see how it goes. Okay, so I want to show this box statement here. So what is this? We have a cross-intersecting family such a way that n sets, and both the family A and family B is a one intersecting family, and this large is about n squared. Okay, so so we make the lower bound in 3 steps. The function is monotone increasing, and the first step is, we already have seen that it's always at least n. Good. So we have a lower bound n, but we want a lower bound n squared. Okay, so I want to discuss only this problem. We are looking for 2 families, A and B, n uniform. Both are one intersecting, and both are size of n squared. Now, so both are like a projective plane. Okay, so if the size is n squared, then the degree cannot be larger than n, because, well, so it's very close to the projective plane. Actually, the whole there's a large literature of these kind of results, that if you have many pairwise intersecting sets of size n, then and we have almost n square of those, and we really have a projective plane. But we can't allow the projective plane because we have an extra condition that every A set has a pair, disjoint, and that's a crossing set, a covering set of the other projective plane, other almost projective plane. So it looks impossible to make it, but it's not so. So in the second step, if we make the same kind of product we have seen, we take our friend, an affine plane. An affine plane has q+1 directions and parallel classes. And every parallel class, we take a copy of the double star. So actually, these squares and these squares are the same sizes. So this is also q. So we take one parallel class and other parallel class, and the idea is that when we define the set A, this is the red line here, extended with some member of the double star, and the set B is the next line which parallel to it. So actually, in this side, we use these edges many times. But you see, when we had this condition, we have no condition between A and B, just that they are cross-intersecting. So we want two projective plane-like structure which are cross-intersecting. And in this way, we got two Q element sets, and altogether we have Q square of these pairs. So now we already have a quadratic lower bound for the function we are investigating. And then, and that's the last step, we do the very same thing again. So we take, okay, this is not FQ now, but FP. So we take a prime, which is close to n. But we take a prime, which is close to n, and take the affine plane of size p, well, p square elements. And then instead of the double star, we use the previous example, what we can do. And just match the pairs and got the nice thing. Okay, so that's the end. I mean, so here the point is that we created two almost projective planes, which are kind of cross-intersecting. Okay, so that was fun, and that's my last. Oops, what direction I go? Yes, that's the end. Okay. Thank you for the attention.
Thank you, Zoltán.
Thank you very much. Any questions? There are some questions on the chat, in the chat room. I don't know if...
Oh, I haven't checked that one. Probably these exceed my... Here it's getting dark.
I actually have a question about one of the applications that you showed about perfect graphs. Can you maybe say a bit more about that? Meaning, because you went through it very quickly, and I wanted to understand.
Yeah, well, Gasparian's paper available. It's a '96 paper. It was a real. So actually, our proof is not much different what he did. So except I'm sorry I can't find so quickly, but the basic idea is just that we consider minimal imperfect graph and check how the clicks and the independent sets are maximal clicks and maximal independent sets are how they are placed to each other. Let me see, I can't find it was somewhere.
I think it should be soon.
Oh yeah, yes, yeah, it's here. Yeah. Okay, so that's Lovász theorem, and what we prove really is that the corollary, that if it's minimally imperfect, but everything is like that, then how it goes. So it's just so if this statement is true for every subgraph, then you must have those partitions. So it was a really nice thing when Gasparian did this proof without any polyhedral combinatorics or thing. It was published in Combinatorica in the Hungarian journal, a few pages.
Thanks, Zoltán. I'll take a look. And there is one question in the chat. Do you have any further conjectures on the values of M of ABC in specific cases?
Well, I couldn't even prove a polynomial or something. I mean, we didn't really well, we were interested in the 0-1 case, the linear case, because that's what. So originally, this latest research started with click partition, the thickness of click partition, and there naturally linearity and one cross intersecting comes up. So we did not work on that one. Didn't really work, but yeah.
The linear algebra part, it just like in Fischer's inequality, maybe the one if you replace by a constant, then.
Yeah, so it's if it just have upper bounds. So yeah, so
that's only true if there is only one intersection, I guess.
Yeah, if it has only one intersection, then maybe the linear algebra works. Yeah. So obviously there are a series of problems here which might be investigated, and maybe some of them are nice, some of them are just work. But if one come up with a nice construction, like how to, I found attractive this question that to place two projective planes next to each other, kind of. So So probably, yeah, we all have our favorite tools and just try it.
Thank you very much indeed.
Thanks, Zoltán. It was very dense and interesting.
Thanks again. Thanks for the invitation.